large corrections still at the Planckian, still later than the Planckian time. So regular hydrodynamics cannot have emerged at the Planckian time. Question?
Old information of the quasi-particle decay rates and all of this universal information.
Yes, very good question. So indirectly, yes, it must. Of course, no. So more precisely, I'm saying that collectively, these coefficients hold that information. Okay. Now, the biggest correction will come from the longest lived, maybe quasi-particle or non-hydrodynamic excitation, which, may not have an imprint on D prime. This thing might be very small, and that bound might be very weak. It will have an imprint somewhere, but that at least gives you a bound. They're not equal, but they're one bounds the other. Yes. So it actually doesn't matter because you're losing control regardless of. So they all have different powers, and this gives you timescales at which you're losing control. I'm even being conservative, right? I'm saying at times of when this is order 1, you've already lost control. You've well lost control. So this is okay. This is still a slightly complicated bound. But Marvin had a very nice idea, which he presented in his poster, which is that there are other corrections that are also inevitable. And these come from KMS that we saw when we were building our action. KMS led to a bunch of constraints. It fixed higher derivative terms in terms of lower derivative ones. And loosely speaking, it leads to corrections that have the Planckian time here. Okay, so I'll let you talk to Marvin for details, but there's another source of corrections, the diffusion, which are also inevitable. And there's a way to make this a little bit more precise. Let me just say it vaguely like this. There are corrections coming from KMS, which force the equilibration time to be larger than Planckian. Okay, so hydrodynamics emerges late in weakly coupled systems, but it can't emerge arbitrarily soon in strongly coupled systems. Now, is this experimentally relevant? Yep.
I also think of it as like if I try to use the hydro EFT for omega sort of much larger than T, then I can't ask conditions, like the derivative expansion breaks.
Right. Yeah. So you could ask. There's, I think, a formal question. You could ask: are there ever systems, and SYK type systems might be an example, where there is a kind of quantum hydro EFT that has a much higher cutoff, where you keep all these omega over T terms to arbitrary order, which has another cutoff that's super Planckian. So that, I think that's an interesting question. It's a little more formal question, right? The experimentally relevant question is more, are there corrections? And these corrections are inevitable at the Planckian time. Yes?
So that's kind of similar to what you have for regular bound, which is just that your framework is falling apart, but it doesn't really bound physics.
The framework is diffusion. If diffusion is falling apart, that's great. That's very exotic physics. But when you have a DC resistivity, you probably have diffusion. Yeah, so I am assuming that the hydro EFTs apply. That's true. So that's a good point. So you could say, in 10 years, maybe the next person will come and say, we'll give it as another example of the limits that. But hydrodynamics, is expected to apply everywhere, whereas semi-classics is expected to apply in a limited context. So is it experimentally relevant? It's not exactly the observable that de Banjan wanted. In fact, these bounds, to make them sharp, as you may see from Marvin's poster, it's nice to work in time domain, which is maybe not the most natural thing for most experiments, although it depends. So is it experimentally relevant? Well, yes, in the sense that, this is bounding very conventional observables, okay? Dynamical correlation functions as a function of time. But is it relevant to, let's say, linear in T or things closely related to linear in T? So there, it's less directly tied, but there's still an analogous statement we can make in frequency domain. Which brings it close to what the Banjan wants. Which, so you could basically just Fourier transform everything I've done. The field theory, gives you predictions in any representation. And you'll get corrections to observables. Okay, you'll get corrections to the optical connectivity from higher derivatives, from loops, from all these things. And the EFT helps you parameterize these corrections. So they'll come with many coefficients. Okay. So this is an expansion that's controlled at very small frequency. Okay. And the same way that we've bounded the coefficients of the corrections in the time domain, you might expect that it would lead to a bound in for the coefficients in frequency domain, which are simply related to the previous coefficients. Okay, and so roughly, so getting the order one factors is a little bit hard here, but the time scales, the content of the statement is that the time scales suppressing higher order and frequency corrections, to DC resistivity at very small frequency, must satisfy a Planckian bound. Okay, so if you draw an optical connectivity, maybe you'll have, a Drude-like, but it doesn't have to be, behavior. So, and let's say, temperature is around here. So, so what I'm saying isn't actually telling you something about the actual value of the DC conductivity. It's also not, strictly speaking, telling you the width has to be Planckian or bounded by Planckian. What it's strictly speaking telling you is about the leading small frequency corrections. So if you can measure very small frequency, how the DC connectivity is approached, that these corrections come with at most Planckian timescales. Okay, but if things are simple enough, you might hope that these corrections are related to the width of these observables, but that's not a rigorous statement.
Wait, on that part.
Yep.
Yep. Right.
Uh-huh.
Sigma omega.
Uh-huh.
So, I mean, I guess maybe it's not inconsistent.
Sigma of omega, so 2D-CFT at zero density.
Yeah.
Yeah. So
like maybe certain like.
I think it has some. It doesn't have a beautiful Drude peak, but it will have some frequency depends, right? It will have some.
Maybe pathological holographic example.
Where it's constant. Yeah, that's right. So let's see. Yeah. So okay. Maybe in most situations, these coefficients will be so indeed. I think that's an example where you precisely have this type of behavior, right? It's a little bit less marked, but you have features around h bar omega equals t. right? Oh, you're saying where it's exactly flat. Yeah, yeah. Okay, maybe that would be worth looking at these. I should say, so I should also say that I swept the Fourier transformation under the rug, which is a little bit subtle and has order 1 numbers, which I'd have to think about if that bound really translates into a bound on all these coefficients. I'm not completely sure, but yeah, I would be interested in that example.
Yeah, I mean, I might be missing.
Okay, yeah, but definitely generically, they have a behavior. They just look not much is happening, but there's some features around this, and so you expect an expansion in omega over t. Okay, so I think I will stop here and take questions.
This way is easiest to do.
So it depends a little bit on the experimental setup. In cold atoms, time resolution is pretty nice. But there are also some techniques like near field techniques where you actually can visualize things in time domain where that, you could potentially imagine trying to look at things there. Yes.
It's actually quite the AC is going to be extrapolated to zero frequency pretty well.
Yeah.
It's just a simple Judah. So in that case, if you can put a bound on right close to the very low limit of frequency range.
Yeah.
And then at the same time, it's the AC is extrapolated as well. Does that mean that this theory already is a bound on the?
So I mean, I think morally, yes. So if you knew somehow that this was the answer, right, then indeed these power law corrections at small frequencies would exactly, yeah. Sorry, I guess I need like this. Well, let me just write a sigma dc 1 plus omega squared tau transport squared. So if you knew you had a Judah-like conductivity, then indeed the width is the coefficient of these corrections. But so experimentally you never know what the function is. But and let me say, actually theoretically you actually always know it's never Judah. Because of these corrections. So we know there are corrections like this, which might be hard to see, but so just even in principle, it's never Judah. Judah conductivity does not exist in interacting systems. These might be small corrections, but yeah. But it's, maybe yeah. Well, sorry.
Generic effective field theory predicts its own demise. And I always phrase that as a bound on some physical quantity, or is that particular to this hydrodynamics?
Well, I would say it's a bound on its cutoff, on the cutoff of the effective field theory. Yeah. Yeah, so there's been some work on generalized hydrodynamics, which is is supposed to apply to integrable systems that have many conserved quantities but are not completely free. And so actually predicting correlation functions in these systems is hard, even though they're integrable, and their generalized hydrodynamics can be helpful. In a sense, it fits in this general paradigm of just saying, you'll have a field for every conserved quantity. Yeah, it's another example of that.
So it's like hydrodynamic approaches effectively. How would it be able to accommodate, let's say, transport close to an interface? Is the question of adding extra terms because you have broken the symmetry, or is there something that is?
Yeah, so it depends a little bit on the length scales that you're talking about, right? So if you have, a box, but the box size is much larger than the thermalization length, then you could just use these hydrodynamic effective field theories in a finite volume. You just put the effective field theory in a finite volume and get predictions.
Whereas old bath, like you said, energy, the transfer with the outside, like some cold atom system. There's a hydrodynamics different there. I think like there's some actual like energy conservation doesn't give it a different about it.
Right. Yeah. So I mostly had in mind closed systems, but a lot of these ideas also apply to open systems with some modification. You know, it depends what's happening with the bath. Are you exchanging energy? Are you exchanging charge? And you know, but a nice thing of this framework of, you know, strong symmetries, weak symmetries, and their spontaneous breaking is that it really kind of universally applies to open systems, closed systems with slightly different symmetry breaking patterns. But everything kind of, you know, it's a formalism that kind of captures all of these. Right. Yeah. Right. Right. Because you can exchange energy, for example, with your bath. Let's say. Right. So you know, in correlated systems, we care about usually energies conserved to good approximation if you isolated your material well enough. So energy is the charge in that case, the conserved charge in the sense. Yeah. Yeah, so here, I really just followed what we did in the time domain. We had done this careful analysis of how big corrections are, how they scale in time, depending on what you know, operator, what correction, what irrelevant correction you add to the effective field theory. This is how it looks in, you're asking about the log? Yeah, so the dimensional analysis tells you it's omega to the d. That actually looks analytic, and it turns out it's not analytic, but it's made non-analytic by a log. Yes. This one is a two-loop correction to diffusion.
So in your scaling analysis, I mean, there's nothing guaranteeing that there isn't maybe another fixed point that's, for example, large or something. That,
yeah.
Since we're not doing fixed point near a critical point, there's nothing guaranteeing that the fields have to be smaller. Right?
So you're asking what would happen if I take my system far out of equilibrium?
I mean, when we do Ginzburg Landau, the fields are small because of those two critical points.
Yeah, here it's the same. The effective field theories you can think of as critical points. They're just Gaussian critical points. So I'm not saying it's the only possibility in the universe. I'm saying it's a consistent possibility, right? That has you can think of the effective field theory as a fixed point that has only irrelevant corrections. So it's a very stable fixed point. But indeed, other things can happen.
Yes, what
happens? So okay, let's see. I don't know much about unstable fixed points in high enough dimension. But one thing, so certainly in one dimension, a lot of interesting things happen. The Navier-Stokes equations turn out to be unstable against fluctuations. So that's an example of an unstable fixed point. Navier-Stokes. It actually doesn't describe fluids in one dimension. It flows to KPZ dissipation. So that's a situation where you have two fixed points, right? KPZ, which is stable, and diffusion, which is unstable.
You could also have that this is a stable fixed point and there's another stable fixed point very far away.
Yes. Yeah, so mapping the landscape of these things, right. I see. So
there's a new fixed point that's not a Gaussian fixed point, and it looks like a critical point and has divergent viscosities.
In two dimensions, or two dimensions?
2 dimensions.
Yeah.
You know, also some of the dipole
Mm-hmm.
With Danko and Swami, that it doesn't need. So I had a question. Maybe I missed something, but understand what nonlinearities are you looking at to get these corrections for?
So I'm looking at all of them, but it turns out that the leading one just comes from temperature or chemical potential dependence, density dependence of your diffusion constant.
But why does not introduce new coupling constants? That's not part of you.
It introduces new coupling constants that are part of the effective field theory.
That are what?
That are part of the effective field theory.
Okay, but somehow you were, maybe I misunderstood, you were saying that all these corrections that are completely expressible in terms of the diffusion theory.
That's right. So the diffusion theory is expressing them. But when these corrections are becoming order 1, there's going to be higher loop corrections with the same vertices that are also going to be order 1. So we're completely losing control. You see, so we can predict them at very late times where they're small.
But the time
yeah.
at which those corrections become large.
Yeah.
Depends on those couplings.
Depends on those couplings. That's right.
Okay.
So that's why the first bound we got depended on these on D prime in the middle board. Yeah.
That's the D prime.
That's the D prime. That's the D prime.
So that's a good coupling.
That's new coupling. Now, it turns out there's also high derivative corrections that come with the Planckian timescale.
Any other questions?